The back EMF constant, Ke, is one of the most misunderstood numbers on a motor datasheet. Formally, Ke is defined as E divided by omega m, the ratio of induced voltage to mechanical speed. In plain terms, it tells you exactly how many volts a motor generates for every unit of speed it spins at. Why does this one number matter so much? Because unlike other specifications on a datasheet, Ke is the single most useful value for actually selecting a motor to match your power electronics. Over the next 4 slides, we're going to unpack exactly why that's true, starting with a comparison most engineers get wrong. Here's a question I like to ask on exams. Does a higher torque constant mean a motor produces more torque? Almost everyone says yes, and almost everyone is wrong. Look at this diagram. On the left, a slot wound with 6 thick turns. On the right, the same slot wound with 26 thin turns. Both slots have exactly the same cross-sectional area, the same fill factor, the same current density, and that's the key. For a fixed rotor and stator, the product N times I is locked by the slot fill factor, and the current density, it cannot change. So when you increase the number of turns to raise the torque constant, Kt equals T over I, you simultaneously force the achievable current down by exactly the same factor. Net torque capability doesn't improve at all. Ke, by contrast, scales cleanly with N alone, with no current term to muddy the comparison. That's precisely why back EMF, constant, not torque constant, is the number engineers actually trust when selecting a motor. So if Ke is the trustworthy spec, how do engineers actually use it? Look at this chart. Back EMF rises linearly with speed. E equals Ke times omega m. Every motor design deliberately keeps that rising line just under the supply voltage ceiling, right at the motor's rated speed. That gap labeled headroom isn't wasted design margin. It's exactly what the current control loop needs to keep working properly, even at top speed. Once you fix K to hit that target, something important happens automatically. Because Ke and Kt are numerically equivalent in SI units, the torque constant gets fixed too. You don't get to choose both independently. And here's a subtlety worth remembering. Most datasheets never show this equivalence explicitly because manufacturers often specify Kt and Ke using inconsistent units, which hides the relationship in plain sight. If Ke and Kt aren't independent, and Kt is actively misleading, what should you actually use to judge motor performance? The answer is the motor constant, Km, defined as torque, divided by the square root of I squared R, the copper loss. Here's why this ratio is so powerful. Torque scales with current, but resistive loss scales with current squared. Taking the square root of power in this ratio cancels the current term out completely. Km becomes independent of both current and the number of turns. As N increases, Kt goes up, but resistance goes up with N squared, and those two effects cancel exactly, leaving Km unchanged. So what actually moves Km? Air gap flux density, rotor outside radius, and the square root of wire volume. Practically, that means shrinking the air gap using stronger magnets, or growing the rotor and copper volume, not adding more winding turns. Let's close with 3 practical takeaways. First, you can measure Ke yourself, right now, with nothing more than a multimeter. Spin a disconnected motor's shaft at a known speed and read the open circuit voltage. Divide volts by speed in radians per second, and you have Ke directly. Second, if you've worked with RC or drone motors, you already know a version of this constant. It's called kV, rated in revolutions per minute per volt, and it's the same underlying physical idea as Ke, just flipped. Speed per volt instead of volts per speed. A high kV motor is simply a low Ke motor. That's a real example right there, an FPV drone motor rated in kV on its own datasheet. Finally, Remember the three jobs these constants perform. KE matches a motor to your supply voltage and rated speed. KT is numerically tied to KE, not an independent design lever. And Km is the one you actually use to compare torque efficiency between different motor designs. Three numbers, three very different jobs, and now you know which one to trust for which decision.